Welcome back to Calculus 2 practice problems. We are looking at the ratio and root test. These are two unique tests and they both have their place in our toolbox for solving these series and determining whether they're convergent or divergent. With the ratio test, if we're given some series from 1 to infinity of a sub n, and we tried a few other tests, maybe they're not working, maybe we don't know what test to try, we can look at the ratio test where we look at the next term in the sequence over just the nth term in the sequence, and we'll take the limit as that approaches infinity of that. So this is very helpful for factorials, with which we will look at. If that limit is less than 1, it will be absolutely convergent. If the limit is greater than 1, it'll be divergent, and if the limit equals 1, the test is inconclusive. We'll have to try something else. So absolutely convergent. Well, you have to now state that it's absolutely convergent, because in the last video we looked at alternating series, which can sometimes be conditionally convergent. So we're not going to deal with any kind of conditional convergence with the ratio and root test. The root test is very similar, by the way. It still follows these same 3 rules, just with a root test instead. We'll look at that later in the video. But how about this? You can see that it's very helpful for factorials, because since the limit as n approaches infinity, the absolute value of a sub n plus 1 over a sub n is equal to L. We want L to either be, once again, less than 1, greater than 1, and not equal to 1. So what is a sub n? A sub n is 2 to the n over n plus 2 factorial. What is a sub n plus 1? Just means everywhere you see an n, put in an n plus 1. So you have 2 to the n plus 1 over n plus 1 plus 2 factorial. So it's actually equal to 2 times 2 to the n, right? We could bring out that 2 over n plus 3 factorial. Now let's take the limit as n approaches infinity of a sub n plus 1. We said that was 2 times 2 to the n over n plus 3 factorial. And we're dividing that, we're taking the ratio of that over our a sub n. So you're about to see why this is so helpful with factorials. So when we're dividing two fractions, we can do a keep change flip, right, and do 2 times 2 to the n over n plus 3 factorial. We can now flip the second fraction and change it to multiplication and do n plus 2 factorial over 2 to the n. So maybe you can see why this will help with factorials, but 2 to the n will cancel 2 to the n. What is n plus 2 factorial over n plus 3 factorial? I'm going to take that to the side. N plus 2 factorial over n plus 3 factorial is actually very easy. N plus 2, n plus 1, n, and then keep repeating that, right? For a factorial, you just multiply by the next decreasing term, right? N plus 2 factorial would be n plus 3, n plus 2, n plus 1, n, and all the nth terms. And as you can see, they cancel each other. That's kind of cool about these nth factorials. All we're left with is n plus 3. So we can say that n plus 2 factorial over n plus 3 factorial is just equal to 1 over n plus 3. So the factorials cancel each other. We were left with a 2 over n plus 3. And we can drop the absolute value sign in this case, because we're only plugging in positive values of n. That will always be positive. What is the limit as n approaches infinity? Let's see. Plug in infinity, and you'll get 2 over infinity, which is equal to 0. So we're used to that being an issue, right, in the videos before this one and the last one. But 0 is less than 1, right? So we like to see a 0. We like to see, since 0 is less than 1, this is absolutely convergent. Since the limit, to recap, since the limit of the next term in the sequence over just an nth term was equal to 0, and since 0 is less than 1, we could say this is absolutely convergent by the ratio test. It's pretty cool. So we mainly use this with factorials and exponents because they're pretty easy to work around. You have an n plus 1 in there. How about this one? Let's try this one. I like to just do my a sub n and then my a sub n plus 1, 6 times 6 to the n over n plus 2 squared, or cubed. And I can take the limit as n approaches infinity of a sub n plus 1, so 6 times 6 to the n over n plus 2 squared, or cubed. And instead of dividing that by a sub n, I'm just going to multiply it by the reciprocal of a sub n, like we did in the last video, or the last problem. N plus 1 cubed over 6 to the n. As you can see, this 6 to the n is going to cancel this 6 to the n. Now, what are we going to do about the n plus 2 cubed and the n plus 1 cubed? So these are actually not as bad as looks, because as we're going towards infinity, remember this is going to become like an n cubed plus blah 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 blah, and the top one's going to become an n cubed plus a whole bunch of stuff that doesn't matter when we look towards infinity. All we really care about is that n cubed and that n cubed, the first terms, and they cancel each other out. As we go towards infinity, that ratio is just going to approach 1. So let's look at what's left. All we have left is that 6. The limit as n approaches infinity of 6 is just equal to 6. 6 is greater than 1. So what do we say happens? When the limit is greater than 1, the series is said to diverge. So this is the ratio test in action. It's pretty cool. So in this one, we have an alternating case, right? This alternating term. How is that going to affect it? Well, really, we can leave it out, right? Let's look at the limit as n approaches infinity, because we're going to take that absolute value, right? So no matter if those negatives contributed to an overall net negative or positive ratio, right? We're just going to take the absolute value anyway. So let's kind of ignore those alternating terms and see what happened. If we do, maybe you're seeing the pattern, we're doing the absolute value of n plus 1, or a sub n plus 1, so it would be n plus 3 over n plus 1 times n plus 2 times the reciprocal of a sub n. Maybe you're seeing the pattern, how we can do it quicker. What is all this going to equal? Well, there's an issue here, right? Because all of this is kind of just going to become, we have an n squared over an n. It's just kind of become an n. And this one, we kind of have a n over an n squared. It's just going to become 1 over n if we break all those math rules as we're going towards infinity. So when you multiply them together, you're just going to get 1. And what do we say happens when the ratio test or the root test equals 1? It is inconclusive. So we have to figure out a different way. I just wanted to show an example of how it could be inconclusive. This is when the limit equals 1. We have to show another way how this is convergent or divergent. So we could also look at, because of that negative, the alternating series test. What was the alternating series test? The alternating series test, like we did in the last video, let's take the limit as n approaches infinity of everything besides the alternating part. Remember, that could be simplified to just 1 over n. A sub n could be simplified to 1 over n, right? The reciprocal of this, which is 0, so that's a check. And is it decreasing? Yes, it is decreasing, because just plug in into this. Just plug in a number. Plug in 5. You're going to get 7 over 5 times. When you plug in 5, you're going to get 7 over 5 times 6. 7 over 30. Now let's plug in a different number, a later number. We want that fraction to be smaller. So instead of plugging in 5, let's plug in 8. When you plug in 8, you're going to get 10 over 72. Type these into a calculator. You'll see that as you keep going through the series, it's decreasing. So, because of that, we know that it's convergent. Right, we looked at it in the last video. In this case, it's really conditionally convergent, / absolutely convergent. We can prove which one by looking at it without the alternating term and trying to solve it that way. But let's just, not in this video. And if you want to figure out how to determine whether it's conditionally or absolutely convergent, you can watch the last video. But really all it asks us is, was it convergent or not? So yes, it is convergent, but by the alternating series test, once again, we could prove if it was conditionally or absolutely convergent, but these problems are just asking us to determine convergence, divergence. We proved that it was not divergent. Okay, now let's look at another example of ratio test. Hopefully by now you're getting pretty good at this. If you take the limit as n approaches infinity of plug in n plus 1, you're going to get 2n plus 2, right? Because if you have a 2 times n plus 1 in there, you'd have a 2n plus 2 factorial over plug in n plus 1 in there, multiply by the reciprocal, and let's see what we get. Once again, this is kind of just going to cancel with this as we go towards infinity. And what does this factorial over this factorial turn to? Well, this will become 2n plus 2 times 2n plus 1 times 2n factorial. Just keep decreasing it until you can cancel something out. So all of that's just going to become is the limit as n approaches infinity, the absolute value of 2n plus 2, 2n plus 1. Plug in infinity, you're just going to get infinity. Is that an issue? No, because infinity is greater than 1. And what do we say up here in the beginning? If the limit is greater than 1, it is just divergent, right? This is not to be confused with the divergence test. We took the limit as n approaches infinity, and it equaled something that was not 0, right? So it diverges by the divergence test? No, because this is not a sub n. This is that ratio of a sub n over a sub n plus 1 over a sub n. So we're not going to use the divergence test here. Because it's greater than 1 is the reason why this limit showed divergence. So I think we're good on the ratio test. What about the root test? Well, like I said, it's very similar. We have the same rules, and we're still taking a limit as n approaches infinity, except all we're doing is taking a sub n and taking the nth root of it. So it's very straightforward, and it doesn't come up too often, so I'm just going to show one example. These are the kind of problems where they're useful when you have like e to an exponent. So you might start with a divergence test. The limit as n approaches infinity of e to the negative 3n is e to the negative infinity, which is equal to 0. It's not alternating, so we can't do anything with that. That test is inconclusive. You might say, what now? You could do a ratio test, this. Well, because it has n in the exponent, what we can do is the root test. Let's take the limit as n approaches infinity of the nth root of a sub, not a to the n, a sub n. So limit as n approaches infinity of the nth root of e to the negative 3n. You see what we can kind of do with this now is cancel out the n's, right? The nth root of something to the nth power will just leave you with e to the negative 3. What is e to the negative 3? Is that a value bigger than 1 or less than 1? It's certainly not 1, right? So we got somewhere with the test. The root test is pretty cool, but we don't really see it too often. But let's see, we're left with 1 or e to the negative 3, which is less than 1, right? Because e cubed is equal to 2.7 repeating cubed, right? So it's somewhere between 8 and 27, right? 2 cubed and 3 cubed. Let's call it probably around 24, 25. And 1 over 24, 25 is 0 point blah, 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 whatever. We just know that it's less than 1. What do we say when the limit was less than 1? If the limit is less than 1, it is absolutely convergent. So we'll say this is absolutely convergent by root test. So now we have a multitude of tests. Let's think we have the geometric series it's not really a test, but if you can match it to the geometric series form, you'll know if it's convergent or divergent. We have telescoping series, we have p-series, we have the integral test, we have, what else do we have? We have the alternating series test, we have the direct comparison test and limit comparison test and the ratio test, finally the root test. So we have quite the armada of tests, and we're really not going to need any more than these 6 or 7. Right? We will look at in the next 3 videos, the final 3 videos of the series, Taylor series, or first Taylor polynomials, then power series and power series with Maclaurin series. But the point is, we're not going to need any more tests. So this is kind of like the last test, and they all each have the purpose, right? Ratio tests are good for factorials, and root test is good for anything with the n in the exponent. And we drilled the comparison tests and the alternating series test pretty hard. So now we are getting good at determining the convergence or divergence of series using the ratio and root test.